What's up? Huh? Manchester United win ah? Watch TV right now ah? Oh, okay. Hey. Have you ever had a similar situation like this, where you're on the couch, surfing the net, and you have to turn on your television or your remote controller for simply out of reach? Look no further, we have the right solution for you. The National Instrument NI is here to make your life easier.
Hi, I'm Calvin.
And I'm Rong. For this assignment, we are required to use our notebook or PC to program in LabVIEW and link up with the NI via a USB cable.
I'll be showing you the hardware components necessary for this setup and also briefly explain the hardware connection to the MyDeck. Lastly, I will explain how we actually save the individual TV signals from the TV remote to the computer using LabVIEW.
And I'll be showing you the block diagrams of our simulated remote controllers for the Panasonic TV remote and the remote control helicopter, and subsequently demonstrating the results of our effort.
So what we have here is MyDeck, which is a pretty cheap data acquisition device. Now this tool will allow us to measure and analyze the signal received from the TV remote control. So for this assignment, we decided to use one of our home appliances, which is the Panasonic LCD TV. Basically, just like every other remote control, it has the infrared LED that transmits signals to the TV receiver itself. Now the infrared LED is actually flickering at a carrier frequency at around 38 kHz or 40 kHz, depending on what kind of remote control. So basically, we want the MyDeck to actually measure this TV remote signal. So we use this photodiode IR receiver, which can actually helps to demodulate the signal from the TV remote control. Then the demodulated signal coming out from the receiver will be transferred to the MyDeck to be analyzed. Now let's take a quick look at the connection diagram for the receiver wiring. Now the MyDeck 5V DC voltage can be used to power up the receiver, and its output voltage from the receiver is then connected back to the MyDeck's analog input 0. So we use an infrared LED to connect to one of the analog output pins, which is A01. Now this is actually given by the Digital Signal Processing Lab. Now however, we find that the signal from the LED was actually quite weak. Now this is because the MyDeck analog output has a voltage range of plus minus 10 volts with a maximum output current of 2 mA only, which is quite low. We have to place it very close to the TV. So we actually purchased another infrared LED from Simlim Tower. Here, as you can see here, it is actually coated with a transparent plastic, which is better because the TV receiver can actually receive it much clearer. And also we actually bought an LM741M. Now what this does is actually we can use this as a voltage follower to actually increase the current output from the analog output pin.
So as mentioned, I'll need to amplify the current output of the IR LED. So I use the plus minus 15 volt from MyDeck to power up the op-amp. And I will connect the analog output 1 to its non-inverting pin. And so forth, the output of the op-amp will be connected to the infrared LED. So let's do the connection. In our LabVIEW program, we have created a 3-tab control system. The first tab represents the GUI of the modified Add Control button. The second is the GUI for the Panasonic TV remote control, and lastly, the GUI for the helicopter remote control. Let's go back to the Modified Add Control button tab. The purpose of this GUI is to allow us to read and save the signal for each remote control pressed. In this text box over here, we can set the number of the samples to be written. This will determine the number of cycles of the signal received. For example, if I were to key in 10,000 samples, I could only get one period of the signal received. Let us test if we are able to pick up any infrared signal transmit from the TV remote control by pressing one of the buttons. So as you can see, the graph shows at least a cycle of the signal is being received. If I set the number to 25,000 samples, I can receive twice the period of the signal received. In this text box, we can specify the destination where you want to save the signal at. And here is the Enable Write button, which will allow us to save each individual signal of the TV remote. So in this case, we want to save the signal as a LVM file in the Save Signal folder located in D drive. While pressing and holding the TV remote control button, I click the Enable Write button once to capture the signal. With this newly created LVM file, we can now emulate the previous TV signal. This block diagram shows the overall design of the modified Add Control button. We use DAC, Assistant, Express VI to read values from the analog input pin 0. This is the numeric input to set the numbers of samples. And here, we use a comparison Express VI to invert the signal received. Then the inverted signal is then fed into the write to measurement file Express VI for the purpose of saving different signals. To make it write once and save into a local directory, we created an Enable button and a file path name entry. This block diagram represents the design of the dynamic tab control system. If you notice during runtime, when I click each tab, the size of the GUI changes accordingly, which means I can actually configure different height and width for each tab.
Since we know that the protocol for television remote controllers uses a carrier frequency of 38 kHz or 40 kHz, we tried to identify the actual carrier frequency used by our own remote controller by dividing the 38K and 40K over the number of cycles for the period of one sample. We counted a total of 54 cycles for our sample of ones and zeros, but we could not get a whole number from either of the division. We then decided to use the trial and error approach, which was more straightforward. We added a control knob in the front panel that allows us to gradually increase the frequency of the carrier signal while we constantly transmit the IR pulses from our setup to the television. The results of our trial actually showed that our television accepts any frequency between 38K to 40 kHz. Let me now demonstrate the TV remote controller that we have created. This is our TV remote interface. This is the carrier frequency control, the signal strength control, and the 7-segment LED display. This is our TV remote control. This graph shows the demodulated TV signal, and this one shows our transmitted signal. Let me now click on the power button to turn on the TV. Currently we are at channel 1. Let's switch to channel 2. Channel 3. Let's try the up button to switch the channel. Now let's try going to the video. Now let's go back to TV. Now we will try freezing the screen. unfreeze, freeze, unfreeze, freeze, unfreeze. This portion of the block diagram shows our Panasonic TV remote controller. Each of these buttons corresponds to the buttons on the actual TV remote controller itself. And each of these read measurement file components retrieves the previously stored modulating signal and passes it into a sub-VI that I had created. This sub-VI basically takes in the boolean value, the modulating signal, a generated carrier signal, and outputs the transmitted signal waveform. When a true is received from the boolean parameter, it will activate the case structure, and the modulating signal is multiplied into the carrier signal, and the final output is transmitted using the DAQ assistant. This arrangement ensures that the signal will keep transmitting as long as the button is clicked, and will stop transmitting when the button is released. The transmitted signal is then returned back to the main VI to be displayed. I have also added two extra control components which allow users to change the carrier frequency and amplitude, which will in turn reduce or increase the output voltage and power consumption. We have also added a 7-segment LED display to show the channel number selected. That's all for our TV remote. Now let us move on to another one of our creation, the remote controlled helicopter. This is the front panel of our helicopter remote controller. We have the 5 buttons over here: hover, forward, backward, left and right. This is the acceleration indicator, and here we will see the transmitted signals. So now let us test the sensitivity of our remote for the helicopter. So now I'll be pressing the left key, the right key, up, and forward, backwards, left, right, left, right, and hover.
Okay.
Looks good. Again, let us first take a look at the block diagram of the helicopter remote controller. The carrier frequency used by this remote controlled helicopter is exactly 40 kHz. We also added an acceleration indicator over here. Similar to the TV remote controller, we have buttons and read measurement file components corresponding to the controls of the helicopter remote. The difference is, here we have also added a specialized key binding function to control each of the buttons. For this remote, we have the hover, forward, backward, left and right buttons. And in this event structure over here, when we detect a key down event, we send a constant true value into the corresponding local variable. As you can see, we have a key assigned to each of the 5 buttons. And each time we detect a key up event, we will send a constant false value to all the buttons. This will ensure that the signal will stop sending when the key is released.
So we hope that you have enjoyed the whole video.
And we would like to thank Prof. Gan for giving us the opportunity to work on this hands-on project where we learned many interesting and fun aspects of embedded system.
We also like to thank Mr. Muhao for replying all our emails and also guided us throughout the whole entire project.
Hey, Kelvin.
Yes?
Prof. Gan sent us one email.
What was it?
See.
Oh,